tonight's lesson plan is how to do even chamfers around the barrel of a part. It's just, not only is it nicer looking, but if you're in medical at all, you're definitely going to want to do this, only because, again, if the part doesn't look pretty, the surgeon won't use it. I've got plenty of experience with that. I worked in a hospital for a couple of years before I got into machining, and working in the OR. If they didn't like an instrument, they'd just chuck it over their shoulder. So one of the things that we can do here is to make sure the part looks good. And that's what the cross-hole chamfering can do for us. Now, what you're looking at here is our ellipse calculator. What we're looking for is the diameter that the feature resides on. In this case, the stock diameter is 1 inch. And then we need to know the size of the hole that we want to chamfer. In this case, it's a 1/4 inch hole, okay? Once we have these numbers, we then build an ellipse. And again, I'm not working off a solid model. This is just in 2D. So on the CAD side, I will build an ellipse based on the length and the height that was generated from the calculation in my ellipse calculator here. So the length is going to be 0.25, the height's going to be 0.252. I'll add those values into here, and then I'll put the ellipse, I'll center the ellipse over the hole where it's been drilled. Okay, that's why I have my Z and C here. I can always drag and drop the data in there if I want to. I can transfer or translate, so I could leave this at Z and C0 and then take it and drag it into position. But in this case, I put the ellipse at the position that it should be in here. Now, when you unwrap geometry from a solid model, and that's what I've done here, in many cases in a mill cylinder window, when you unwrap geometry, you're going to see some of the geometry has been disconnected. And the reason for that is the x-axis is C0 in PartMaker, and this circle right here, this drilled hole, was at a C value of 0. So it took half the hole at 0 and then projected the other half of the hole at 360. All right, so in a mill cylinder window, the origin is C0. Anything below is positive 360. And you can see that in the stock. C0, negative 360. So we unwrap a total of 720 degrees to ensure that if your machine can only work with positive or negative C axis, we can still create the feature for you and get it onto your machine. Now, when it becomes separated like this, we're going to use the translate function here. So I'm going to select this top half, and I'm going to translate it with a distance method. The horizontal distance will be 0. We're not moving the hole left or right. The vertical distance now becomes the C-axis angle. That's the one thing you want to keep in mind when you're in mill cylinder. And since I want to wrap it around to the other side of the part, I'm going to translate it 360 degrees. I click on the translate button, and you can see it will connect up anything that's been disconnected. Okay, so in this case, what we did, we used the chamfer tool, and I did put a small diameter on the bottom there so I could get the tip of the tool off the edge of the part. Using the contour mill strategy, the X surface is the radius of the diameter of the part, the X depth is the chamfer depth. Once I've got those values set, I can apply and close and run my chamfer. Okay, I just chained the circle here. Let's go ahead and chain that and run the chamfer. Now I do have some regular standard chamfer drill and drill cycles so you can see what the difference is. Let's select OK here and show the finished part. And the drilled holes that are just using a standard spot face, the result is a thick and thin chamfer. But using this technique where we use the C-axis to keep the tool coincident with the edge of the part, we can get an even chamfer on the OD of the part, even without having the solid model. If you are drawing without the solid body, please let me know so that I can send you this ellipse calculator if you want to use this technique. I do have sample files that are all zipped up and ready to go. All you need to do is send me an email saying, hey, Phil, can you send me the best practices class on OD/ID chamfering? and I'll send you off all the sample files and the strategies and instructions on how to create them. This is probably the easiest method if you're going to use a 2D chamfering technique without a solid model. Okay, so let's just close this puppy down. And let's look at working with a solid body. Okay, so let's go ahead and open that up. And this is working with a solid body. And I just want to check to make sure that all my tooling is set correctly. Tool properties looks good. Okay, that's good. All right, now for this, I'm going to use both for the OD chamfering, like if you're just going to project onto that surface, we can just use a regular old chamfering tool. Okay, so we can use a standard chamfer tool for this. And how this works is, again, we're in a mill cylinder window. So what we need for the mill cylinder window is the OD, or the diameter of the feature. Okay, so here's the feature. This is the diameter that the feature resides on. So whatever this value is, right now 3675 is the radius. So the diameter is going to be 735. It is really important that you get the correct diameter. Whatever the diameter that the feature lives on is the diameter that you need to use. Because from there, what we're going to do is we're going to project or flatten out this diameter here. And we do that by transferring unwrapped geometry. So let's see how that works. Just get rid of this guy here. So I double click on the surface. I transfer the unwrapped geometry as arcs into the 2D window. And again, this hole right here is split by X vector, which means that C0, half of it shows up at C0, half of it shows up at 360. So I will transfer that. I'll just take the top half here. And again, I'll transfer it down. 0, 360 plus, translates that to the bottom half. And now I've got my arcs the way I need them. Next, we're going to create what we call a surface project technique. So instead of using the 2D profile group, we're going to use a new surface group. And we'll just unlock that. So the first thing we need to do is to select the tool. And again, let me check, turn off the process table there so I can actually let the tool get selected. Again, with an active process table, you're not going to be able to do much editing on the front end. So this was actually a chamfer tool, so you will switch over to a chamfer tool and then select the tool or add a new tool, okay? Once you've got the tool set, the next thing that we need to do is we need to look at the projection technique itself. We're going to be taking a 2D profile and projecting it down onto a 3D surface. This technique is going to be using a mill ZY plane, although we could use mill cylinder to get a more accurate projection. So that's what I'm using. I could work with a mill ZY plane because surfacing allows the tool to rise and fall on the edge of the part as it transitions through the curvature of this large surface. Mill cylinder, though, just gives you a little bit more accuracy, so that's what we're using here. And the key is to let the system know how much of a chamfer you want. So when you open up the options page here, again, surface projection is a very simple technique. We don't need a lot of surfacing information. What we need to know is the depth of the chamfer. And in this case, I want a 10,000ths chamfer around the part. So I'm going to actually use a negative value. This is one of the few places in PartMaker where you actually have to use a negative number. Most of our other strategies just require positive values, a start point and end point. Let's see, for drilling, you can see that we don't have any negative values in here. They're all positive. The system knows what to do with the values though. But with surfacing, we do need to tell the system that we're working below the surface, and that's why we're using a negative here. A positive number will keep the tool up above the surface by whatever the value is you enter. A negative value will push the tip of the tool through the edge of the surface, and that's what we need to do here. So I'm going to make a 10,000ths chamfer. Okay. Now, once I've got that done, the next thing I need to do is to select what I want to project onto the part. So in this case, I could individually select these holes, and that's exactly what I'm going to do. Chaining in a chamfer scenario is slightly different than finding the center of the hole for drilling. So I'll pick this one and the next one, the next one, and finally the last one. We'll take this flat geometry and wrap it onto the part. I'm just going to turn off the stock motion and slow the tool path down so we can see this. And go ahead and run it. So right now we need to calculate it, but as you can see, it's going to create an even chamfer all the way around the part. And I'm projecting onto that surface to get that. So with solid models, your chamfering techniques become a lot easier because of the fact that you can work off the solid itself. You can project onto the solid model. Without the solid model, you have to use the 2D method and use the ellipse calculator. So those are the methods for doing OD chamfers. They're pretty straightforward. Now the ID chamfers, they become a little bit harder to do. And I've got two samples here. The first sample is for a flat bottom where we can just position the tool and run a 2D tool path, and then a surface project pattern that will create the chamfer on the inner edge here. All right, so let's look at the flat pattern first. What I'm doing here is I'm determining what the depth of the tool should be. And then in the chamfer method itself, I'm offsetting the hole diameter by a value that will allow me to use the upper edge of the lollipop cutter to cut this bottom edge, but not have the offset so far that the shank is going to rub onto that surface right there. Okay, so let's take a look at the tool. You can create ball and or lollipop cutters, I guess is the best way to put it. I don't know what the actual technical term for it is. I've always used a lollipop cutter. So we create a slot mill to do this. The key to creating the lollipop cutter correctly is to make sure that the diameter value and the height value are the same, and the corner radius is half the diameter here. Okay, and then whatever the shank value is, right now it's 50 thousandths. So let's figure out how close we can get to the edge without messing up the part with the shank of the tool. Once I've got these numbers in here, if I do a shape preview, you will see the lollipop cutter. Okay. So if I take 125 diameter for the sphere minus 50 thousandths for the shank diameter, that gives me a total value of 0.075. If I divide that by 2, I know that I've got 37 thousandths from the edge of the ball to the edge of the shank. That distance is 37 thousandths. So what I want to do is when I offset the hole for the ball mill, I want to make sure I'm not offsetting more than 37 thousandths. So let's take a look and see what I did in this case. Okay. So what I did in this case, this is the original hole diameter. This is my offset diameter, and I offset it by 25 thousandths, which is well under the 37 thousandths clearance. So I took this and I offset it 0.025 and created what I'm going to be using to drive the tool path. Okay. Next, how do we calculate for the depth of the tool? How do I get the tool through the center of the part and get the depth correct so that when I do touch this edge, I've got the correct area of the ball mill, the lollipop cutter cutting on that edge. So the first thing I did was determine what this thickness was between this radial value and the flat. And that turned out to be 93 thousandths. Next, I added the total diameter for the tool itself, which is 125, okay? Add those two together, 0.093 plus 0.125 gives me a total value of 218 thousandths. Now we offset the hole by 25 thousandths, so we need to adjust the tool up 25 thousandths to get the edge of the tool to cut on the hole. That's where this 25 thousandths comes from here. So if I take this number 218 and minus this number here, I'm going to get a value of 0.093. I rounded it up though, 295. It should be 0.093. That's the number I'm going to use in my page. So when I create the tool path, the X surface, again, this is the radius of this surface. The total depth in this case is 0.192. Make it 1925 if you want to be hyper accurate. But again, this is an edge break. I'm not really worried about the size of it as long as it's scaled correctly. Very rarely do I see a edge break with a value on it, especially an ID edge break. If you put an edge break on there, it's going to make everybody happy. If you do need to accurately hold the edge break, then I take these numbers out to 4 decimal places. Okay, so that gets the tool depth correct. Next, I need to figure out how do I do a tool entry. And what I can do here is use a little formula to find the center of the hole. Okay. So that's what I'm going to use for my lead in, lead outs. All right. $118.75. So we've got a 237.5 diameter. What we're going to do in the lead in, lead outs, we're going to use the diameter of the hole minus the diameter of the tool, divide that by 2, and that's going to be a line length. That's basically how you find the chamfer value here. That's what I did. If I take 0.2375 minus 0.125, close parentheses, divided by 2, that's going to give me the value that I want to use here. Okay. In fact, I'm going to move that over just a little bit. But that's how you find the center of the hole. Okay. And then, of course, the lead out is going to be the same. Set your angle at 90 degrees. So if I've done this correctly, the tool should find the center of the hole, move down the distance as required, step over to the geometry that I chained, and cut the inner edge and back out. Again, back to the center of the hole and retract. Okay, so again, what we want to do is find the diameter of the hole and then offset that value by a number that's less than the clearance between the edge of the lollipop cutter and the edge of the shank. In this case, it was 25 thousandths. And then when you calculate the tool path, you're going to add this thickness together along with the diameter of the lollipop cutter, and then subtract the amount that you offset the original geometry by. Once you've got that calculation set, find the value that you need to enter into the X depth here, apply and close, making sure your lead in lead outs are good, and you can chain the outer geometry and run the toolpath. And then for the other side, it's just a matter of duplicating the process one time at 180 degrees, and I've got the two flats done. Now, for the radius edges here, we're going to use the power of the geometry of the actual solid modeling capability to create that. There's no way that I can project through surfaces to find this edge here. So the strategy is to create an OD chamfer feature and then adjust the solid model so that the tool will go through the center and run it on the ID instead of the OD. Now that requires a little bit more information. And again, I've got the instructions up here, okay? First, let's look at how I set up for the ID chamfering. Again, having more, make sure that when you're going to offset the cutter. Now with the projection technique, it's the center line of the cutter that we're projecting. That's why the tool path is on the inside here, because it's the center of the tool, not the edge of the tool. So what I did was I figured out how much I need to overlap the tool. In this case, I overlapped at 32 thousandths instead of 25, just so you could see that you don't have to have a single number. You need a number less than the clearance between, again, the edge of the tool and the edge of the shank. Once I found that clearance, I created a circle that equaled the diameter of the tool. Then I used that to find the center point to create a radius. In this case, it matched the tool. The radius equals the radius of the tool in this case. What I'm doing is I'm finding the center of the tool, center for the edge of the tool to do the chamfer. This is actually the center of the tool right here. The blue is the cutting edge. This is the shank. And as you can see, the shank will clear the edge of the hole right here. That's what I'm looking for. I'm looking for clearance between the shank and the edge of the hole that I'm actually doing a chamfer for. So once I've got that center point here, I use that center point to determine what should this size be. And in this case, it just turned out to be 0.0625. So I built a arc at 0.0625 and use this to drive the tool path, okay? So that's the geometry required to drive the tool path. Now let's figure out how we change the value to get an OD chamfer to an ID chamfer. And again, this took a little while to figure out. I spent a lot of time on this. I'm trying to get this figured out, but we've got a really good process now. So what we're going to do again is we're going to take the difference between the tool radius and the hole radius, which is 32 thousandths. Then we're going to take this number here, which is the thickness between here and here. Okay, again, I'm looking for that distance. In this case, it's 0.117. I'm going to add to that value the diameter of the ball. So 0.117 plus 0.125 equals 0.242. At this point, I want to subtract the offset value, which was 32 thousandths. So minus 0.032 equals 0.21. Actually, it comes out to 0.209. So if we do that projection here, now that we've got the number, what we need to do in this case, let me just go to that ID chamfer, and I just want to check the view. Yeah, it's the Y value that I'm looking for. So what we're going to do here, we're going to actually project this solid model down the distance I want to go. Okay, so again, with the surface calculation here, it comes out to 242 minus 032.5. We're looking at 0.21. So we're actually going to go into the setup dialog box. I'm sorry, the edit part coordinate system, set part origin, and I'm going to move the Y value by what I calculated here, 0.21, and set that. You can see how it dropped the center of the solid model. So now I can actually do the OD edge here and create the chamfer on there. Okay, so if I go to the ID chamfer here, I select the process. Let's go ahead and unlock this. And it runs the ball on the outer edge there. All right. Now here's the key. Once you've got this set up, you're going to lock the tool path. We are not associative to the geometry. So once we lock the tool path, that tool path is going to stay in that position. The only other thing I need to do is to look at the options for my lead in, lead out. Because again, I'm trying to find the center of the hole. So I'm going to lead in 60 thousandths at an angle of 90 degrees. And I'm going to use those same values for the lead out. And that's what these orange lines are right here. Okay. We've got the system set the way we want it. We lock the tool path. And then we come back to the edit part coordinate system and we set Y back to where it belongs. And now the tool does the ID. Now you can size the chamfer by projecting further down or further up. Okay, so let's see what this looks like with the process table. And again, let me just make sure before we, okay, I got that one locked. Yep, everything looks good. Hang on a second. Take a look at that tool path there. Don't want to spend all day just shaping that interior there. That's all. There we go. So is anybody here doing medical components or aerospace components? improve the look of your parts, especially for medical. All right, and if you look on the inside there, you can see the chamfer. Now this one we'd have to work on a bit. It is a little bit thick and thin there, but we're still breaking that inside edge. Okay, so that's ODID chamfering.
So what if the wall is the wall of the hole is tapered? How would you do that same thing?
If the wall of the hole is tapered, then I would use the small end of the taper to calculate my tool pass from. It's not a reverse taper, is it? It's not like small here and large here?
No.
If it's a reverse taper, then again, we can do it, but we'd have to use this diameter value instead of the top taper value. You know, whatever we want the edge break on, that's the diameter we would use.
Okay.
And again, if it was tapered, you could just grab the surface and project it as arcs. So it'll give you the right value there. And this is already projected. That's why you're not seeing it. But if I got rid of all that and projected it, you would see that. Okay. Now, when you project, in many cases, I'll project as lines. Notice this is not really an arc here. I'm projecting linear segments. And that's because a lot of machines don't like to do a G2, G3 on an arc itself. In other words, trying to do a G2, G3 here, I've got a transition in XYZ, IJK. If your machine can handle it, great. If not, you have to break lines into arcs so we can get linear segments. We can break lines into arcs with our face options here, but if we didn't want to do it here, instead of projecting the arc, we could just project it as lines and take care of that right off the bat.
So is it better to project as lines than it is to arcs?
It depends on the technique you're trying to use. In this case, I would project as lines because I can get really accurate line segments. Now, what does this do? Generates a ton of code because these are little linear segments with G1, 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 G1. But because I'm projecting as lines and making smaller segments, when I select this to project, it'll be more accurate.
I gotcha.
Okay. And in some cases, it will not project as arcs. Let's see how we do with arcs here. All right, so I'm going to take that surface. Let's project it as arcs. Yeah. Did I pick the right one? No, I'm in the wrong window. Hang on a second. There we go. That's the window I want. All right, let me get rid of this. Take that surface and project it as arcs. In many cases, the arc's going to be broken anyways. It won't be a whole arc because it's got to fit. And that's what the arc function here does. Is we're fitting the arcs here. And the fit tolerance is this value right here. So again, the more accurate the tolerance that we translate, the better the fit. But in many cases, that could create more code at your machine. One of the key features in surfacing on any Swiss machine is how much memory you have on it.
Yep.
And this will include everything you've seen today. It'll include all the cross-hole techniques, the ellipse calculator, the tools and cycles you're going to need. So you can play around with it when you want to.
Would it be possible to do that with a dovetail tool as well?
Yes, you can. You just want to be careful. The dovetail cutter, you want to make sure that you're actually using the sine of 45. But yes, you can do that with a dovetail cutter. Now on the dovetail cutter, depending on the size of the cutter and the size of the hole, a dovetail cutter will follow this here, but it may gouge if the radius is too tight. You know what I mean? Where a ball mill will fall away from there, a dovetail cutter will have a sharp edge. So you just have to make sure the dovetail cutter, when it's cutting this, the edge of the cutter itself is not walking itself into this radius here.
Okay, I follow you.
You know what I mean? It'd have to be a real small dovetail cutter for this one. But yes, you can use dovetail cutters for that, especially on the flats. The flats is dirt simple with the dovetail cutter because we don't have to worry about the edge of the cutter running into a radius. We got plenty of space here.